Okay, we are at section 2.8, freely falling objects. Uh, so, next slide. Okay, Galilee and the Leaning Tower of Pisa. In the absence of air resistance, all objects dropped near Earth's surface fall toward Earth with the same constant acceleration under the influence of Earth's gravity, regardless of their masses. Before about 1600, Aristotle taught that heavier objects fall faster than lighter ones. Galileo Galilei originated present-day ideas concerning falling objects. Legend has it that Galileo observed two different weights, two different cannonballs, dropped simultaneously from the Leaning Tower of Pisa, hit the ground at approximately the same time. Galileo did perform experiments on objects moving on inclined planes. He rolled balls down straight, the slight inclines, and measured distances they covered in successive time intervals. You notice that the reduced incline made it easier to make accurate measurements of time intervals. By increasing the slope of the incline, he drew the conclusion about freely falling objects. So a freely falling object would be equivalent to a ball moving down a vertical incline. Simultaneously drop a coin and a piece of paper from the same height. Coin will always reach the ground faster. Now you crumple the paper into the tight ball and repeat, and both should hit the floor at the same time. Idealized case is the no air resistance, free fall motion. On August 2nd, 1971, astronaut David Scott simultaneously released a hammer and feather on the moon. The objects fell together on the lunar surface. I will include this video and another video of a bowling ball and a feather in the largest vacuum chamber ever. Some of you may have already seen that. Freely falling object is not just for objects dropped from rest. Any object moving freely under influence of gravity alone, regardless of its initial motion, whether it's objects thrown upward or downward or those released from rest, are all falling freely once released. Any freely falling object experiences acceleration directed downward, regardless of its initial motion. The magnitude of free fall acceleration due to gravity, is given by the symbol G, small g. The value of G decreases with increasing altitude above Earth's surface. We'll see why that is when we get to the gravitational force between two bodies. Slight variations in G occur with changes in latitude. It has to do with varying factors, the density of the rock underneath, and there are reasons for the variations. But at Earth's surface, we use a G of approximately 9.8 meters per second squared. If you want to make a quick estimate, just use G equals 10 meters per second squared. Neglect air resistance and assume free fall acceleration does not vary with altitude over short vertical distances. Motion of freely falling objects moving vertically are equivalent to motion of a particle under constant acceleration in one dimension. You can use equations for particles under a constant acceleration model, but instead of X, we're using Y. Modification for freely falling objects, motion is in a vertical direction, the Y direction. The acceleration is downward with magnitude 9.8 meters per second squared. The author here chooses to use acceleration Y equals minus G equals minus 9.8 meters per second squared. There's no problem with using G equals minus 9.8 meters per second squared as long as you stay consistent within the given problem. Time for a quick quiz. What happens to the acceleration of a ball after it is thrown upward into the air? Neglect air resistance. It increases, it decreases, it increases and then decreases, it decreases and then increases, it remains the same. Which of those is the answer? If you said it decreases and then increases, then you may not have been listening to the problem. We're not talking about velocity. We're talking about the acceleration. And the acceleration remains the same. It's always under the gravitational acceleration. Now, if we go and ask what happens to the speed of the ball after it's thrown upward, then, well, I just gave it away, didn't I? Does it increase? Does it decrease? Does it increase and then decrease? It decreases and then increases and remains the same. You throw a ball up, the velocity, you throw it up with an initial velocity, it slows down, reaches the peak, and then comes down. So it decreases and then increases. When you're asking about the speed or the velocity, it decreases and then increases. But if it's the acceleration, what happens to the acceleration? It's constant. Okay, a skydiver jumps out of a hovering helicopter. I need to catch up. A skydiver jumps out of a hovering helicopter. A few seconds later, another skydiver jumps out and they both fall along the same vertical line. Ignore air resistance so that both divers fall with the same acceleration. Does the difference in their speed stay the same throughout the fall? Does the vertical distance between them stay the same throughout the fall? And we'll see that the difference in their speeds remains the same throughout the fall. And we'll see that the first skydiver covers a greater distance than the second. The separation distance between them increases. Okay. Now, a stone thrown from the top of a building is given an initial velocity of 20 meters per second, straight upward. The stone is launched 50 meters above the ground, and the stone just misses the edge of the roof on its way down, as shown in the figure. So this is a straight up and straight down problem. Okay. Because the stone is in free fall, it is modeled as a particle under constant acceleration due to gravity. Recognize that the initial velocity is positive because the stone is launched upward. The velocity will change sign after the stone reaches its highest point. But the acceleration of the stone will always be downward so that it will always have a negative value. The acceleration will always be downward. Choose an initial point just after the stone leaves the person's hand and a final point at the top of its flight. Okay. Use the equation to calculate the time at which the stone reaches its maximum height. Vy final equals Vy initial plus AT. Where Vy final, what's Vy final going to be? It's going to be 0. That's what you, at its maximum height, when it goes the highest, Vy final, velocity is going to be 0. So T is equal to Vy final minus Vy initial divided by the acceleration. So it's Vyd minus Vya divided by minus G. There, the A and the B are referring to the circled A, the circled capital A, and the circled capital B in the figure. Okay, so if you substitute the numerical values, T equals TB, it's 20 meters per second, minus 20 meters per second, divided by minus 9.8 meters per second squared. You'll end up with 2.4 seconds. So that write the 2.4 seconds down, and we'll use that in later calculations. Find the maximum height of the stone above the initial position. Well, now you can use Y max equals YB equals YA, that YA is the initial, plus VX AT plus 1/2 AT squared. We're just using our kinematic equations. Said YA equal to 0, even though you're at the top of the roof, just set it equal to 0, and you'll find how far it went. And substitute the 2.04 seconds, you get YB equals 0, 20 meters per second times 2.04 seconds plus 1/2 gravitational acceleration times 2.04 squared. And you'll see that the minus makes it 20.4 meters. Okay. And determine the velocity of the stone when it reaches, when it returns to the height from which it was thrown. You can use VYC squared equals VYA squared plus 2AY times the distance, YC minus YA, and you'll get 20 meters plus 2 times 9.8 meters per second. The YC minus the YA is 0 minus 0 because it's returning to the same point. That doesn't look right. 40. Oh, yes, it does. 400 meters squared per second squared. It's VYC squared. So then when you go to, that wasn't the final answer. When you go to VYC, you get minus 20 meters per second squared. Now the square root of 400 is not 20, but because we know it's going in the opposite direction, we choose the negative root because we know that the stone is moving downward at point C. The velocity of the stone when it arrives back at its original height is equal in magnitude to its velocity, but it's opposite. It's in the opposite direction. Okay, now find the velocity and the position of the stone at t equal 5 seconds. And we just use this equation, yd equals vyd equals vya plus at, 20 meters per second. That's the initial velocity, plus minus 9.8 meters per second squared times 5 seconds, and you'll get 29 meters per second in the negative direction. And yd equals ya plus vya times t plus 1/2 at squared, the acceleration. That's so ya is 0, 20 meters per second times 5 seconds plus 1/2 times a minus 9.8 meters per second squared times the 5 seconds squared. You're going to end up with 25 seconds squared. And when you work that all out, it's minus 22.5 meters, 22.5 meters below below where it started. Okay. What if the throw were from the 30 meters above the ground instead of 50 meters? Which answers in part A to D would change? None of the answers would change because notice nowhere did we put the fact that we were 50 meters above the ground when we started. So none of that would change. Okay, and that's it for this. The next section we will discuss is the kinematic equations derived from calculus.